again, and it's a pleasure for me to be with you once again. And today's class, I'll be talking about the technologies for simulation of renewable energy conversion system. And first of all, I have for those who don't, for those who don't really know me, I am Robenson Jean, and I am an electrical engineer. I am really involved in the energy sector, and mostly and the part of rural electrification. Also, I'm really involved in energy storage system, wind energy conversion system, and PV design. And then I'm here to share some knowledges related to the technologies for simulation and renewable energy conversion system. But as we know nowadays, the fact is there is a transition that is being made, and this transition it is because of the result that we had nowadays, the sad fact, the sad result that we had by excessive use of fossil fuel, the increasing global demand, and also we're seeing what we have with the global warming and the excess of gas emissions. So one way to mitigate this problem was the integration or the massive integration of renewable energy conversion, or the massive integration of renewable energy sources. But this integration comes with some issues also. And in order to mitigate, there's problems. Many things has been tried, like for instance, the use of energy battery energy storage system in order to mitigate the fluctuation of renewable energy sources. And also there are other techniques like the control system in order to reduce harmonics, to reduce voltage variation, power fluctuations, and but we do know that we cannot try directly a system. So that's why it is important to think about simulation, because the simulation gives us a lot of possibilities, and that's what we will see today in today's class. So now let's see what kind of challenges and issues that we do have in electrical grids. Now, I'm not talking about the renewable energy integration. Now we are going to see the electrical grid itself. For instance, there's a problem of reliability. This problem of reliability is the fact is that sometimes the systems we had, we cannot count on it in every moment because sometimes there are kind of outages that can come, and they are related to peak hour, for instance. And one way to deal with peak hours, it is the integration of backup power plant, like solar power plant, wind power plant, and other kind of renewable energy-based power plant. And also, sometimes we have a flexibility problem in electrical grids, resiliency problem, efficiency problem, also the energy balance, because we do know that the main point for an electrical grid, it is to make the balance between the offer and the demand. And that's right. At power plant, we have the obligation to produce in every moment, and the production should be the generation must be always equal to the demand. So it's like we are following the load. But what happens if sometimes we do not have sufficient energy to supply the load? So we will be in a period of outage, and that's the main point of the integration of renewable energy that help us to deal with peak hours without calling more fossil fuel based power plant, because normally that's what we do. That's what we do. What we do is inject energy from fossil fuel based power plant. But this is another way to increase the harmful gas emissions and also to keep on in the same way. Now, the thing is to think about change. So in order to mitigate the fault, to mitigate the technical losses, also non-technical losses, what we do is integrate renewable energy sources. And renewable energy sources, we cannot say that it is something, it is a holy technique, because there is advantages, there are advantages, there are disadvantages. And as advantages, obviously, there is the environmental protection. And with this, we can reduce the fossil fuel consumption. And it is easier for us to make the energy balance because we can use normally only a renewable energy-based power plant. And when we are in period of lack of production, we can use maybe a backup based on fossil fuel. Also, we can use the energy stored and an energy conversion system. For instance, like there are some country and rural places, the power plant are based on solar, and at night what they use to deal with the night peak is the backup from the battery energy conversion, the battery energy storage system. So we do see that we can make the energy balance in order to always meet the power generation with the demand. Also, we will increase employment, because we have seen in some places the implementation of renewable energy project help to create more jobs, and this will be a way to increase the employment. Also, this is a way to contribute to rural development. But we also have disadvantages. The disadvantages are more related to the intermittencies, the unpredictability, because most of the renewable energy sources are variable, and they depend on the weather conditions. Like if you're in a wind, so obviously it depends on the wind speed. And if we're talking about a PV system, obviously it depends on the temperature. It depends also on the irritants. And there is the question of maturity, because some of the renewable energy technologies nowadays are not yet so mature in order to implement a big power plant based only on a single renewable energy source. But obviously, there are some technologies that are already mature, like wind, for instance, solar, for instance. So, and that's why they are the leader now in the renewable energy sources nowadays. And also there is the problem of low energy efficiency. I think you can figure out that the higher efficiency of a solar panel nowadays is around 22%, 22%. So this means like all of the infrastructure that you will deploy, you will only use 22% of that in order to produce the energy. Imagine that if we could have a solar panel with 50%, it will be very interesting, and we will use the half of the superficie of the space that we use to implement a solar power plant. So this is a kind of disadvantages of solar technologies. And also we have the low capacity factor that is related to the same thing. For instance, imagine and wind. First of all, we are limited by the limit of beds. Due to the limit of beds, we cannot produce more than 57%. We cannot extract more than 57% of the kinetic energy present in the wind speed in order to convert it into mechanical energy. And after, we'll have mechanical loss, electrical loss, and the generator linked to the wind turbine. And after, most of the wind farm, they have only 20% of low capacity factor. So we do see that we have a problem of efficiency and also a problem of capacity factor. And the tendency is trying to increase the efficiency, increase the capacity factor. And also we have the relative high cost of implementation of our renewable energy project. So there's disadvantages, but we can mitigate these disadvantages, and we can mitigate them in the area of research and the design, because in research, thanks to the simulation, we can reach some wonderful results, results that are not expected at the beginning, and that's right. We are giving a lot of importance to simulation. But first of all, let's see what is an energy conversion system. I think in some previous presentation, I already talked about energy conversion system, and now I will make a brief summary of an energy conversion system. An energy conversion system is definitely a set of converters that we have in order to ensure the transformation of the energy from the source and then supply it to the load, like in another form of energy that can be used by the consumers. And it is a very important part of the process, because it helps us to increase the efficiency. Because imagine that if we will inject directly from solar panel to the electrical grid, so this will never be possible, because first of all, solar panel inject in DC, and our electrical grid are in AC. So we need an energy conversion system in order to transform it from DC to AC, and then also to mitigate the variability, because due to the dependence on the weather condition, there are some variabilities, but we can smooth the power curve before we inject it into the electrical grid. So this will help us to improve the reliability and also to have a touch on the control process. Now, we can make a big overview on the renewable energy conversion system. A renewable energy conversion system is not something that we have and that can work under every situation. The renewable energy conversion system depends on the source. Depending on the source, resource we have. For instance, if it is solar, we have to implement a specific component for solar, like for instance, for solar, there is a component that is very important, that is the MPPT tracker. The MPPT tracker is an important component in solar energy conversion system, for instance. And in the wind energy conversion system, sometimes we will need a transformer, we will need a rectifier in order to put it into DC in order to make the voltage regulation. After, we'll transform it into AC energy again with an inverter and then pass it through some LC or RL filter in order to reduce the harmonic distortion, and then inject it at the point of common coupling into the grid. So we do see that the energy conversion system depends on the source that we have. So over there, is the screen? Yeah. Over there, we have on the right side, we have the solar source, wind, that can be hydro, also biomass, geothermal, tidal, and then the renewable energy conversion system plays a role like an interface between the electrical grid and the source. Now, the main component of a renewable energy conversion system is, first of all, the source, obviously, that we are seeing. Sometimes we'll need a generator. For instance, in a wind energy conversion system, the wind turbine is linked with a generator, and this generator can be from various types. For instance, a mostly used generator is the permanent magnet synchronous generator. That is very easy to manage because it is easier for maintenance. Also, we'll need a regulator, for instance, in solar energy conversion systems. We do need a regulator that has an MPPT tracker integrated in order to track the maximum power point. Also, we have the converters. The converters are very important. They are DC-DC converter, DC-AC converter, AC-DC converter. It depends. It depends on the type of source. For instance, if we have a battery energy storage system into the energy conversion system, we will need DC-DC converter like buck converter and boost converter in order to synchronize the voltage of the battery with the voltage of the DC link. Also, we will have, anybody has a question? Okay, I can make it clear for you. If anybody has a question, you can ask the question, and I will stop in order to answer the question. Okay, thank you. And finally, we have the control system. The control system helps us to process for some to process to some challenges like power smoothing, voltage regulation, also harmonic distortion mitigation, and other things that are very useful. For instance, if if we have to manage things like load leveling, power smoothing, those things, we are going to deal with them with the control system. And also the control system help also to 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 stay close to the references, because in an energy conversion system, we have references. We cannot operate without references. For instance, we have to respect the requirement for the grid code, like at the point of common coupling. The point of common coupling is the point where we are going to inject the energy into the grid. And at this point, we have to respect the voltage, the reference voltage of the electrical grid, the frequency, and also the expected power. So if the operator of the grid expect from us like 10 megawatt, we cannot supply 5 megawatt. We cannot supply 5 megawatts, and neither we cannot supply like 15 megawatts. So we have to respect the requirements, and the control system help us to stay close to the references. And now we're going to see another thing that is very important in a system. I say a system globally, even when I'm talking about a renewable energy conversion system, but this is important for a lot of systems. And the life cycle management of a system, we have a first part that is the research part, where we are going to process to the modeling of the system, the analysis of the system, like go from physical model to mathematical model. And then we will have a model ready for simulation. So now we have a design. So with this design, we can make simulation, various types of simulation. And then after this step, we have the development and manufacture. After, we can go on the field for construction and installation. And after this step, it is the moment for operation. And if we say operation, we will need maintenance through the lifetime of the system. And at some point, we will have to change some component. We'll have to update the system. We'll have to adapt the system to new conditions, to new requirements, or we'll have to adapt the system to unexpected conditions or unexpected needs or demand. And after, when we come to the head of time of the system, we'll have to think about the dismantling of the system. But the first point, it is our interest today. The first point talk about research and design, and it is at this point that we are dealing with the modeling and the simulation. Now let us see what is the importance of a simulation. First of all, a simulation is like immersing oneself in a virtual environment, like a computational environment, in order to imitate the real system behavior. And this process passes through the modeling of the system. First of all, the physical modeling, then the mathematical modeling, and we will simulate the characteristic of the system. And after, we will try it under specific conditions that can be extreme conditions or realistic conditions. And then we will analyze the results. And through this analysis, we will see if our system has a good answer, or we will see if we can improve it, and we will see if we can change it completely. So this is a process that will give us a lot of important outcomes. And as important for the simulation, it is the fact, obviously, it helps us to avoid direct experimentation. Like, for instance, if I have to implement a solar energy conversion system, the first thing that I will do, I will not go to buy physical components in order to delve into the experimentation. First of all, I will go in a virtual environment in order to implement the system and try to see if my system works correctly on the normal conditions, also on the extreme conditions. For instance, if I have a system to simulate now, I will try it on the extreme conditions like on the low irradiance and high irradiance. And also, I will try to see the behavior of my system when I am away from STC conditions, like when I'm away of 25 degrees. Like I will try to see if the temperature increase up to 30 degrees, 35 degrees, for instance. It is extreme conditions, okay? And this will help us also to minimize the risk, like a risk of accident, risk of losing some equipment. And also this will reduce the cost of the research, the cost of the modeling. And obviously this will help us to avoid unnecessary issues, and it will help us to optimize the design. And sometimes in simulation, we do have some results that are previously unexpected. Sometimes we come with very interesting result, but it is only trying in the simulation, and we discover some interesting stuff. So that's all the importance and the advantages of the simulation. And there are various types of simulation. There are real-time simulation and non-real-time simulation. When I'm talking about real-time simulation, the fact is sometimes in order to process to a simulation, and due to computational limitation, we cannot implement a real-time simulation on our computer. And it is for that reason, we'll have to use discrete time. The discrete time is the fact that the data that we will store the data every single step. And the step can be defined as every 50 milliseconds or every 100 milliseconds. So it is a way to make a type of discretization of the time in order to reduce the memory use of the computer. And this will make it easier for us to perform our simulation. I don't know if anybody of you used to implement a simulation on MATLAB. You can see that when you put the simulation on continuous mode, it takes more time to run than when you use the discrete mode. So this is a kind of limitation. But when we are dealing with real-time simulation, we will need another component like an external computer, and we will use the memory of this external computer. And this computer is like a super computer that help us to perform the simulation at the same time with the clock time. Okay, so this will help us to try some more realistic behaviors, and also under real-time simulation, we can have online simulation or offline simulation. When I'm talking about online simulation, it is the fact that sometimes you can change some parameters at the meantime the simulation is running, but in offline you cannot change anything. You have to wait for the simulation duration, and after you will analyze the result. But in online simulation, at the meantime the simulation is running, you can change some input and see how the system react with the perturbations, and you can see it instantly in the result. And as a type of simulation, we have software in the loop simulation, when we use a software that is integrated into the system. For instance, if I want to implement a battery energy storage system, I can simulate all the other components, like, for instance, if I have a wind turbine, I can have a virtual wind turbine, a virtual generator, virtual converters, a virtual electrical grid. But for the battery energy storage system, I can implement a block, and this block will be a software that represents the battery energy storage system. And through this block, I will see how it interacts with the rest of the system. Also, we have model in the loop, we have processor in the loop, hardware in the loop. The hardware in the loop is when we integrate into the simulation a real component. For instance, we can integrate some wheel rectifier, wheel inverter into the simulation, and see how the simulation react with real component before we go into the real world, where we will use real components for everything. So these are various type of simulation that we can use in power system. Now let's see some common simulation software. This depends on the part where you are in the conversion system. Remember that in the conversion system, we have the sources, we have the energy conversion system itself, we have the converters, and we are the part of integration into the grid, the part where we are dealing with the point of common coping. For instance, if we are talking about the power systems themselves, there are MATLAB, ETAP, LabVIEW. These are very useful software. Me, for instance, I use LabVIEW, MATLAB in order to simulate my systems. And if you have to deal with a solar conversion system, so you will have to deal with the PV design. And for PV design, a wonderful software is Homer Pro. Homer Pro gives you the possibility to simulate the bus, the AC bus, the DC bus, where you can inject power from DC sources, like from battery, from PV system, and also the AC bus where you can inject power from AC sources, like the electrical grid. And also, if you have a wind turbine, you can inject it directly to the AC bus. And Homer Pro gives you the possibility to design the converter or to select converters that already exist on the market. And at the end, Homer Pro gives you the possibility to make a resume where you will have you can see the installation costs, the operation costs, and also if you have to make change through the lifetime of the system, you can simulate this. And there is a helioscope. Helioscope, if you want to deal with shading analysis, or if you have if you want to know what is the required space to implement a PV system in order to have a given power. So helioscope is the exact software to use. There is PV SolStore. And there is Samuel. The Samuel is very useful because Samuel help you to deal with PV system, wind energy system, also geothermal system, tidal system, and if you have to make a real-time simulation, to perform real-time simulation, the software is RTLab. The RTLab is a software from a Canadian company. The name of the company is Opal RT. And Opal RT will provide you real-time digital simulator. It's like the super computer in order to perform a real-time simulation, and also the software that that can match with MATLAB simulation. For instance, if you already had a simulation on MATLAB, you can use the same simulation on MATLAB and implement it into the RTLab, and then you will only need to respect some procedure related to the real-time simulation you want to perform. Remember that as real-time simulation, you can perform software envelope simulation. Let us see. You can perform software envelope simulation, hardware envelope simulation. If you want to integrate hardware, if you want to integrate some processor, you can perform processor envelope simulation. And for all of this, you will need a real-time digital simulator and also the RTLab as a software. There are others alternatives, but the RTLab is a very good one. And if you have to simulate a wind energy system, there are Samuel. It is from the Noel company, and there is a Grid Lab, SimScales, and for transmission and power generation, for power transmission and power generation, there is PSSE, that is a power system simulator for engineer. It is from Siemens. And also you can deal with Big Silent Power Factory, PSCAD, that is power simulator. CAD. And for renewable energy solution, we have Novopo, PVCs, Homer, we have IOGA. IOGA is a software that help you to simulate the load and the power sources that can be sources from thermal, solar, and also wind. And it help also to make to simulate the energy balance, like to make the balance between the renewable energy sources and also the load that we will have. And we have other type of software like GSOL, ESYS, eSIM, a lot of. So the fact is, we do not intend to master all of this simulation software, but the fact is to identify the one that you need, in order to master it, and then to use it at your convenience. For instance, if you're involved in power electronics, the best software for you is MATLAB, LabVIEW, and also I can say ETAP. For instance, if you want to perform things like, okay, let us see some application. For instance, if you want to set up the installation cost of a wind farm, you can use Omepo. Look at the interface of Omepo. You can see at the left side, you can simulate the integration of conventional power plant, the integration of wind turbine, the integration of PV system, the integration of energy storage system, and you can simulate the load, you can simulate the converters, and then it will give you a result where you can see the the situation of your system, the installation cost, the operation and maintenance cost. And if you have to change some component in 5 years, you will know the cost. In 10 years, you will know the cost. So you can make an economic analysis with this, and also a technical analysis. So this is the interface of MATLAB, for instance, and you can see through the MATLAB, you have a library that is very rich, and there are a lot of components. If you are in robotics, if you are in aerospace, if you are in electrical, mechanical, you can use MATLAB to simulate your system. And I have some applications of the common simulation software that we've seen. There is the optimal design of controller parameters. You can perform this with MATLAB. Load flow analysis. You can perform this with ETAP. Modeling of system. You can perform this with a software like LabVIEW. Short circuit analysis. A white one is the software called ETAP, also to perform single line diagram. You can use software like AutoCAD, Lab Report. You can use LabVIEW, reporting, writing, LabVIEW, voltage stability, MATLAB, dynamics and junction stability. You can use RTLab and reliability assessment. You can use software like Samuel software. Now, let us see a case studies. This case studies is related to a wind energy conversion system. Look, this was the thing that I was talking about. And then energy conversion system, you have the source. Let me use the laser. Okay, this part is related to the source. So now I'm dealing with a wind energy conversion system. This is the model. The model is just to see how I will represent my system. So I will try with this, and then I will I will analyze the result in order to see I can make some changes, or if the prior model was a good one. And here I have the source, the wind turbine, and after the wind turbine give me mechanical power, and this mechanical power, I can transform it into electrical power through a generator. And this generator can be a PMSG, like a permanent magnet synchronous generator. It can be a squirrel cage synchronous generator, and it can be a double-fed induction generator. We have commonly two types of generator: the induction generator and the synchronous generator. And as the generator is supplying energy in AC, so we can use a rectifier. The rectifier is in order to convert the AC current into DC current. And when we convert it into DC current, at this part where we have the DC link, this will help us to make voltage regulation, and also this will place will play a role like decoupling. The decoupling is like if I have a perturbation here, so the perturbation will not go to the grid. And if I have perturbation into the grid, the perturbation will not go into the wind turbine. So that's why we transform the AC power into DC and then make voltage control, voltage regulation, and then we transform it again into AC through an inverter. And this inverter is controlled, and the control signal comes from the control system. And the control system work with the feedback that we have. Because here you can see at the point of common coupling, we have the meter, and this control, it is in order to ensure that we are respecting the requirements of the grid. Like if we respect the voltage, the voltage of synchronization, the frequency, and also the expected power. And through this, we have this closed loop in order to control the inverter. And here we have the filter, and the filter, it is in order to reduce the harmonic distortion. Remember that the tolerance for the harmonic distortion is no more than 5%. If it is more than 5%, the operator of the grid will not accept it because it will be a kind of energy of poor quality. So we have to inject the right voltage, the right frequency, and the right power, and with good quality. So this was the model, and then after the model, if I pass through MATLAB, I have this. Because MATLAB gave me through its library the possibility to implement the generator. In this case, we have a permanent magnet synchronous generator, and also it gave me the possibility to implement the rectifier, and I can choose if my rectifier will be with MOSFET or with diode. I can choose if it will be a controlled rectifier or uncontrolled rectifier. And here I have the DC link implemented, and the main component of the DC link is a capacitor. The capacitor plays the role of a buffer, like an energy buffer. Sometimes it stores energy, sometimes it releases energy in order to smooth the voltage and also to smooth the power fluctuation. And sometimes in order to increase this buffer rule, we can implement an energy storage system. And the energy storage system will help us to deal with energy balance, power smoothing, peak shaving, load leveling, things like that. But now we only have this that plays the role like an energy buffer. And then we have the inverter, where we transform the energy from DC to AC, because we do know that in order to inject into the grid, we will need an AC voltage. So this is the filter. This is an RL filter. And here we have the measurement system, where we have a voltmeter and ampere meter in order to know at every moment the voltage, the three-phase voltage and the three-phase current, and then to perform the control. And through this control, that depends also on the DC link voltage, you can see the three input, the DC link voltage, the three-phase voltage, the coin voltage, and then this will help us to generate the control signal for the controlled inverter. And this control signal help us at every moment to generate the voltage that is required by the grid, and also the power required by the grid, and the right frequency, that is 60 Hertz. And this was an example of the simulation of wind energy conversion system. Now, After the simulation, we have the validation process. The validation process is in order to know if what we have done complies with the reality. Like if it is a good thing. Like for instance, the fact is on the simulation we are in the theory, but when we go to validation, we go closer to the practical world. So this is a step in confirming the effectiveness of the integrated wind energy conversion system. In other words, I can say the accuracy and the consistency of the results obtained on the defined conditions will be assessed in accordance with the prior outcomes set in the theoretical framework. So the alternative to the validation process, we can validate through software in the loop, like we perform an offline simulation on MATLAB, and then we'll make the validation with software in the loop simulation. And also we can do it with hardware in the loop simulation, like integrating wheel components in order to see if our simulation work exactly with the wheel component. In the case of software and developer, what we'll need a model. And after the design of the model, we'll make the simulation based on this model. And after, we will integrate the main component as a code. And then we'll need a workstation. And on this workstation, we do need installed the real-time simulation software. And we'll need a real-time digital simulator, and also we'll need a methodology. But the methodology depends on you. The methodology will depend on you. Everybody can have his own methodology. So here you can see what you will have on the workstation and what you will have on the real-time digital simulator. And this a kind of representation of the process. It's like you have your simulation on the workstation, but the simulation is not running on your own computer, is not running on your workstation, but the simulation is running on the real-time digital simulator. And according to OpenRT, you can perform power system simulation, robotic simulation, automotive simulation, aerospace simulations. So there are a lot of things that you can do. It depends on the field in which you are involved. And my advice to you is to follow the trends because the world is now changing. We are running after more computational capacities, faster simulation software, and also the type of software that you will buy depend on your needs and on the challenges also. And another thing is try to keep you updated, with the version and also with the software and trends. So this is my advice to you, like to learn more and more software, because if you're a student, for instance, it will be useful for you if you're looking for jobs or if you're doing your thesis. Sometimes there are some simulation software that can really save your lives. So thank you so much for following with me, and I don't know if you have a question. I'm looking at the chat. Let us see.
Thank you, Robenson. It seems like Dr. Jane has a question. Let's see what she has to say.
Can you repeat for me, please? Let me see.
Dr. Jane has a question? Yes.
Good evening.
Good evening.
In common simulation software, you mentioned the case study, that is a wind energy conversion system, and we have the control. Then under the control, you said filter, DC link, and rectifier. Controller
Yes.
have all this and it controls it. Now, my question is, when you have wind tumbling, which you said is mechanical, does this still goes under controller?
Wait a moment, please. Wait a moment, please. I will ask you to repeat for me, please, because I do not hear you very well. So let me hear you again. Can you repeat again for me, please?
Okay.
Yes.
In a case study of a wind energy conversion system, you made mention of controller, which controls the filter, the DC link, and the rectifier. Then my question, in wind tumbling, which you mentioned is mechanical, does it still goes under the controller for a wind energy conversion system?
Okay. You're talking about this figure, right? Where we have the wind energy conversion system, and we have the several part. We have the wind turbine, the generator, the rectifier, the DC link, the voltage source converter that serves as an inverter, and here we have a filter, and here we have the controller. And you can see that here you can see the sense of the arrows. The sense of the arrows is like we go from the meters to the controller, because the controller is like a system that helps us to have feedback from the system. And we use the feedback in order to generate a control command. And inside the controller depends on how you want to implement your system. Okay?
Okay.
And in order to design the controller, you have to make the mathematical modeling in order to see what are the main components to deal with in order to adjust voltage, to adjust current, because the main control that we do inside the controller is voltage control and current control. Okay? The voltage control is made like, for instance, and the DC link is made to maintain a reference voltage. For instance, in my case, I made this DC link in order to maintain the voltage at this is an example. This is my case. In my case, I designed it in order to maintain the voltage at 600 volt. So at every moment, I have to have 600 volt. So the input of the inverter must be always the same, because if the input of the inverter is changing, the output of the inverter will be changing. But why is this necessary? This is necessary because the wind speed is varying. So when the wind speed is varying, the output of the electrical output of the generator will be varying also, and also the output of the rectifier will be varying. And if I'm injecting a variable voltage at the input of the inverter, the output also will be varying, and I will be injecting a variable voltage into the grid, and the operator of the grid will not accept it. So in order to mitigate this problem, what I do, I make a control system so the DC link will force the voltage of the DC link to be the same at every moment, even when the wind speed is varying, even when the output of the generator is varying. So what I do, I make almost constant the voltage, but remember that the power depends on voltage and current. Like if I'm in DC, power is voltage time current. So if I maintain constant the voltage, what will be varying is the current. So the operator of the grid don't have problem if the current is varying. If the current is varying, we don't have any problem. The only fact is the current must reflect the power. It is right that so the fact is I do not expose the port inside of the controller. Well, I don't know if you allow me to present another screen the with the MATLAB simulation, because inside the MATLAB simulation, you can see what happened inside.
Yes.
I think it is very good to have this kind of curiosity. Yeah, it is very interesting. Let us see that into MATLAB.
Yes, we have, you can present screen share MATLAB.
Do you see my screen?
Yes, we can see it clearly.
Okay, very good. Okay, this is what I was talking about. Here I have the control system. You can see like here we have the inverter, we have the grid, and we have the DC link. So I will show you. Inside my control system, I have this. I come here, and you can see where I put the reference. The reference for my DC voltage. Okay, and what I make, it is a comparison between the read voltage and the reference voltage. And after this, I use a PI compensator, and with the PI compensator, I can send a reference power. And remember that we do have a relationship between voltage and power. So through this relationship, I can extract the current in order to compare the current with the current and the grid. Okay, so this is the current control. So I use the result of the voltage control in order to make the current control. Okay, and then this will help me to send the modulation index. So it is a kind of complicated when you're not involved in this field, but you can see the process is to generate the control signal, like I pass from an ABC reference frame to a DQ0 reference frame in order to make the control. And after I pass again from a DQ0 reference frame to ABC reference frame. So I send the reference control, and then the reference control is sending through the inverter, so I can reach the grid reference. And here you can see the grid reference, because here you can see that you can set the configuration of the grid if you want it in Y, or if you want to imply the ground. And also you can see the voltage, the frequency, and then it is a way to maintain the voltage here constant, because here the wind speed is varying. So when the wind speed is varying, the voltage also will be varying. It is why also in every point of the system, I have some monitoring system, like to see the voltage. Like in the scope, I can see the voltage, I can see the power, and I can see the current, okay? So this is more or less what we are dealing with the controller. So this is an example. Okay, thank you. Thank you, Antonella, for the materials. Yeah, exactly. If you go on the website of Opal RT, you will have much more information on real-time simulation, real-time digital simulator, also the type of simulations like software in the loop, hardware in the loop, hardware in the loop. They are very useful, and maybe it can help you in your thesis and the what the question, please?
We have a Frank Phyllis question, and then we can go with the questions in the chat. And let's see what Frank has to say.
My question is, what do you mean by simulation, size, nature? How important is it? Hello?
Simulations nature. I think you're, let me see.
Size,
yes?
nature.
Do you hear me?
Size, nature. How important is it?
I don't remember if I talk about size nature, but I can answer you. Like when I'm talking about the nature of the simulation, let's see here, for instance,
Okay.
where I talk about the types. Yeah, I talk about the types of simulation because there are several types of simulation. Sometimes you need systems that work closely to a realistic environment, but sometimes you cannot. For instance, if I'm simulating an electrical grid, it is better for me to use a real-time simulation. So let me use the laser pointer. Yeah, if I'm simulating an electrical grid and non-real-time simulation and also offline, the result that I will have, it will be close, but not exactly the same as a real-world electrical grid. Why? Because in an electrical grid, the data is processing every instant. But when I'm in a non-real-time simulation, I'm working with discrete time. Like the data are saving like every step, and the step can be defined like every 50 millisecond or every 100 millisecond or every 60 millisecond. Why? Because if I'm processing a simulation in real time on my computer, I will lose for memory due to the dynamic allocation. Because you can see when if you have a program that is running, if you check your memory, you can see that your memory is full. This is due to the dynamic allocation. And after the simulation stop running, you will see that you will have a lot of available memory. So due to this saturation, sometimes simulation on your computer. If you're working on your computer, it is better for you to perform non-real-time simulation using discrete time simulation. But if you have to make if you want to make the validation, because at some point we remember that I told you that after the simulation, in order to test the accuracy of your result, you have to make the validation. And one way to make the validation, it is to use real-time simulation. So the real-time simulation, you can perform it using a real-time digital simulator.
Kat dan dossier l'autre monde yo te kon lettre de recommandation.
Okay, it's okay?
Yeah.
Someone is speaking Creole. I understand Creole.
We have two questions in the chat.
Thank you, sir. Thank you, sir.
Yeah.
Merci. Merci beaucoup.
Merci à vous too. I'm Asian too. Glad to
Thank
meet you.
We have two more questions in the chat. Let's see. The first one is
Let us see.
from Thomas Okello, and he asked, how far has technology gone in terms of renewable energy supporting the EV industry, this being one mega factor employed to mitigate environmental damage?
I was trying to see the question of Thomas, but I don't see it into the chat. I don't know if you can paste it and into the chat for me, please. Okay. Everyone, okay, from everyone. Can you repeat the question for me, please? Because I don't see the question from Thomas.
He says,
yes?
How far has technology gone in terms of renewable energy supporting the EV industry, this being one mega factor employed to mitigate environmental damage?
Yes. Okay. Obviously, you do know that, but my opinion is shared on this question. My opinion is really broken on this question because using electrical vehicles, the fact is sometimes which type of energy we use to recharge our batteries. We use fossil fuel-based electricity to charge, and the production is production that is generating harmful gas emissions. But the positive things is the harmful gas emissions are generated in one point, but the electrical vehicle is running through the street, through the city without emissions. So we avoid the emissions at one point, but we generate more at the other point. And this is where the renewable energy integration acts like a buffer for this sad fact. When we are integrating renewable energy generation, we are reducing the fossil fuel-based electricity share. And at the same time, we are increasing the renewable energy-based electricity share. And when you are recharging your electrical vehicles, you are using a greater percentage of renewable energy-based electricity. So I think working on this field, like if more and more people are involved in the field of renewable energy conversion system, or power system, for instance, this will help also to increase the renewable energy penetration, and to enhance or to improve the efficiency of the energy conversion system. Because one important thing, it is not the integration of it is not only the integration of renewable energy sources, but also to improve the efficiency of the energy conversion system. Because imagine that if you are producing 10 megawatts and we are losing and the switching loss and ohmic loss 5 megawatt, like 50% of the produced energy, this is not reliable for us. It is not reliable. So the objective is to increase the efficiency of renewable energy conversion system, and at the same time increase the renewable energy sources integration. And after, I think that we can reduce the fossil fuel consumption, and then we'll have a better world, and we will be able to mitigate the global warming, and that's the point.
We have one more last question in the chat. This is from Caleb Desir. He asked, what can be the result if the simulation is run by using improper information such as climate data?
Yeah, very good question. That's why at a point I was talking about, let me see. I don't know if you can see the screen. Okay, that's why in a simulation, you have to analyze the results, okay? And after analyzing the result, if you're not satisfied, you will have to go again into your model. Maybe something is wrong into your model, into your physical model, or into your mathematical model, because the process of modeling is really important. It is an important process, because in the modeling, maybe it is possible that you're not taking into consideration an important fact, an important parameters. For instance, imagine that I'm designing the model of a solar energy conversion system, and I do not take into consideration the effect of the temperature. But we do know that the current, the output current of a PV array varies with the temperature. With a high variation of temperature, we will have different output currents. So if in my model, I do not take the temperature, at the output, I'll have something wrong. So the fact is to well know the field of investigation, because you cannot simulate something if you don't know this thing previously, or if you miss something. So it is important to take into consideration the process of modeling. The process of modeling is very important. And after the process of modeling, you will pass to simulation. And you can see in this, in the case of, in the case studies, you can see what I present first. It is not the simulation. What I present first, it is a schematic diagram that represents my model. Okay. For instance, in the first version of my model, I did not take into consideration the voltage of the DC link. But what happened? What happened is the fact that sometimes I had some fluctuation in the voltage here. So I go again in my model, and I saw that I should take into consideration the DC link voltage, like the input voltage of the inverter and also the output voltage of the inverter. I have to consider both voltage, the input voltage and the output voltage. Okay? And after, I pass to the simulation. And other thing important, it is the methodology. You have to develop your own methodology, for instance. Okay? For instance, as a methodology, you will have to make data collection. Like if you will make a simulation, you will simulate under some condition. It may be extreme condition like extreme wind speed, or normal condition like a daily wind profile, for instance, but you have to analyze this data and the wind speed profile, for instance, and the wind speed profile. If I see that there is a point that is very different from the others, I have a problem in my data. So I have to make a data cleaning before processing to the simulation. I have to make the data cleaning. I have to make sure that my data reflects the realities, and then make sure that my model is close to the reality, that I have taken under consideration all the parameters possible, and then well implemented my simulation, and after analyze correctly the results. And if I have the problem, maybe my problem is into the simulation, and I will look for this problem and then make the correction. And once again, because me in my methodology, I always put an iterative process, because an iterative process will help you to do it again, and do it again, until you will see that you have almost the same result in every step. Okay, and every iteration. And if it's okay, I pass through validation. Okay, I can validate it. Like if I made the simulation with MATLAB Simulate, I will use another process to make the simulation, like to simulate the same system, but on the different platform, like on the software envelope simulation, or using wheel component into the simulation, and then see if the result that I will find is the same, or if it is close to the result that I have with the virtual simulation. And if it's okay, so I can say that my results are validated, so I can go through reporting, publication. If it is for thesis, you can go ahead. If it is for article, you can go ahead. It is the point. But my advice to you, it is to implement a methodology and implement an iterative process into the methodology in order to compare various iterations.
Thank you, Robenson. I think that was the last question. Thank you, everyone. Thank you for your time, for being present today. Remind you that after this class, we will send an email with the certificate of assistance, and you can download it directly from there. Thank you, everyone. See you next week at the same time for another class. Bye-bye.
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 Okay.
Bye-bye.
Thank you.
Bye.
Bye-bye. Thank you.
Bye-bye.
Bye.